Okay, so here, large f of x represents the integral from 3 to x of small f of t dt. And this graph is basically a semicircle connected by two line segments. So part A, find large f of 0. So to find large f of 0, you're simply going to evaluate this integral for x equals 3. So large f of 0 would be equal to the integral from 3 to 0 of f of t dt. Now, we simply figure out what the area underneath f of t, underneath the graph of f of t from 3 to 0 is. But since we're going backwards, we're going to multiply that value by -1. So 3 to 0, we're looking from here to here. So we have this triangle, we have this rectangle, and then we have this semicircle. So let's figure out the areas of those three things. So this triangle, half of a square unit, so this will just be 1/2. This rectangle, 2 by 1 rectangle, so an area of 2. And this is just a fourth of a circle that has a radius of 2 units. So it'll be 1/4 times pi r squared, where r is 2. So 1/4 pi times 2 squared, or 1/4 pi times 4, or just pi. So we'll get the total area is being pi plus 2 plus 1/2. So pi plus 2.5. And that'll give us negative pi minus 2.5. Large f prime of 0. To calculate large f prime of 0, we're essentially going to differentiate this integral, which cancels it out. So then you're just going to have f of 0. Let's recall that integration and differentiation are inverse operations. So basically they cancel each other out, they undo one another. So f prime of 0 is going to be equal to small f of 0. We figure out what the value is by looking at the graph. Or basically at this point over here, it's 0, 3, so that'll be equal to 3. Then large f of 4. Here we again plug in 4 for x in this integral, so we're going to integrate from 3 to 4 of f of t dt. So we just look at our graph, figure out what this value will be, and we have basically a triangle that's below the x-axis. So this will have an area of -1/2, or a value of -1/2, so to speak. Okay, so that's it for part A. All right, part B. Find all relative minimum values of large f of x on the interval from -3 to 4. Okay, so to find the minimum values of a function, you want to first figure out possible critical values. Critical values, let's recall, are values where the derivative is equal to 0 or where the derivative is undefined. Now, the derivative of large f of x is basically just f of x. So let's go ahead, let's write that out. F large f prime of x, it's just going to be f of x. So to find critical values of large f of x, you're essentially just finding where is small f of x equal to 0. Or where is it undefined, but it's not going to be undefined on this interval. So small f of x is equal to 0 over at 3. So this is a possible critical value. So now we want to essentially see what's going on with this function around x equals 3. So in other words, we want to see if large f of x is increasing or decreasing before 3, and if it's increasing or decreasing after 3. So essentially we're trying to see, like, let's pick a value close to 3. Let's pick like large f of 2.5. So f prime of 2.5, and then f prime of, let's just say like 3.5. Now, since large f prime of x is just equal to f of x, we just have to look at the graph of f of x, and then we can determine what the sign of f prime of x is at these two values. So this is just equal to f of 2.5, and this is just equal to f of 3.5. F of 2.5 is going to be, negative. It's less than 0. Oh, no, sorry. F is positive. And after, it's negative. So essentially, let's say if this is our point, x equals 3, the graph is increasing before and then decreasing afterwards. So we actually don't have a local minimum at x equals 3. We actually have a local maximum, and there aren't going to be any relative minimums. So it's a relative max at x equals 3. All right, part C. Find the x-coordinates of the inflection points of large f of x on the interval from -3 to 4. Okay, so to figure this out, we need to study what the concavity of the graph is. So for that, we're going to look at the second derivative of large f of x. So f double prime of x, we want to see what's going on with the second derivative of large f of x. And similar to like when we're figuring out where possible local minimum or maximums are, we're going to figure out where the second derivative is undefined or equal to 0, and then see what's going on around that point. So let's first write what this is. So f double prime of x will simply be the derivative of small f of x. So I'll be equal to f prime of x. We want to see essentially where is f prime of x equal to 0. So where is there a horizontal tangent line? So looking at this graph, there's only really one spot where there's a horizontal tangent line, and that's going to be at x equals 0. Now, it is also undefined, or the derivative is undefined at x equals -2 and +2. But since this is not a smooth curve, these won't qualify as possible inflection points. You want basically the derivative from the left and right to be equal at these points. So all we have to check is over here. So at x equals 0, we now just want to see what's going on with the graph before and afterwards. So for it to be an inflection point, the graph has to change from increasing to decreasing, or decreasing to increasing. In other words, the derivative has to change signs. So if you look at the left here, the derivative to the left, we'll just call that like f. We'll say f prime of -1. The derivative of f prime of -1 is positive. And to the right, let's say f prime of +1 is negative. So since the derivative changes sign at x equals 0, there's an inflection point over here. All right, and the last part, write the equation of the line tangent to a point where x equals 2. So to write the equation of the line tangent, we're going to figure out what the derivative is first at this point, because that'll give us the slope of the line. Remember, we're ultimately going back to like our basic algebra. We're trying to find the equation of a linear function, so y equals mx plus b. So to find the slope, we find the derivative at that point. So we're going to find the derivative of large f of x at 2, so f prime of 2 will be, we already established that this is just equal to f of x, so this will just be equal to f of 2, or small f of 2. And small f of 2 is just going to be equal to 1, because that's just this point here. Then so far we can then write our equation as y equals 1x plus b. Now we have to figure out what the y-intercept would be, so the value of b. So we know that our x value is 2, so it goes through 2. We need to figure out the y value. We need to figure out y value to plug in. So to figure out the y value, we're going to calculate large f of 2, because that's our input for x. So large f of 2, going back to this integral, will be integral from 3 to 2 of f of t dt. So the area between the curve from 3 to 2, the small triangle again, but since we're going backwards, it'll be negative 1 times 1/2, so this would be negative 1/2. And so then our point will be at 2 negative 1/2. That'll be our y value. Now we can figure out the y-intercept of value b by plugging those two values in. We'll have negative 1/2 equals 1 times 2 plus b. Solving for b, negative 2.5. And finally, our equation for the tangent line will be equal to y is equal to 1x minus 2.5. And we are done for that.